Good afternoon, everyone. It's my great pleasure to introduce Dr. Zeng. He obtained his PhD from Department of Statistics in the University of Michigan in 2001, and he's now a professor of Biostatistics Department in the University of North Carolina. He's a fellow of Institute of Mathematical Statistics and also American Statistical Association. His research interest includes precision medicine, machine learning, electronic health records, and high-dimensional data inferences. And today he will talk about using integrating tools to estimate optimal treatment rules using electronic health record data. And let's welcome Dr. Zeng. Okay. Dr. Zeng, is all yours.
Sure, thank you. Let me share my screen. Give me 1 second. Let me move this away. Can you guys see my screen now?
Yes.
Okay, good. Let me make a full screen. So give me 1 second. I try to find the full screen button. So, okay, great. Thank you for the invitation. I'm very happy to see Michigan virtually. I visited Michigan last fall, so but I still had a very good chance to talking to people here. So the talk I'm going to talk about is try to share my experience how to analyze one particular EHR data and using both statistical tools and machine learning tools. And hopefully I can, through this work, I hope you can appreciate the advantage of this one, or maybe advantage from different aspects, including statistical modeling and also machine learning. So I can give a very brief introduction about data we try to analyze and what's our goal here. And also next, I'm going to start to present our methods. The first part is about how we're going to use the statistical models, try to understand the data, especially understand the heterogeneity or substructure, subgroup in the population. And the next one, I'm going to present our machine learning type approach, try to learn optimal treatment rule, because my goal here is like for precision medicine, basically, we want to come up with treatment rule for this kind of, from this data, so that when like new patients come in, you can give the best treatment for this patient. So that's the whole goal we want, hopefully we can do here. And of course, I'm going to show you the results after this application. All right, so the data is from electronic health records data from about 25,000 type 2 diabetes patients. And they had a diagnosis between like January 1st, 2013 until the end of 2017. So the whole range is about 5 years. And this data actually we got is from Ohio State University, Wexner Medical Center Information Warehouse. And we have a collaborator over there, and also they have a clinician team, and we work with them. And one particular question, we talk to them about which kind of feature variable, in this case is biomarkers, we can incorporate into our treatment rule when we make a decision, right? So obviously a lot of biomarkers should be related to type 2 diabetes. So I include some important here. You can see we have a systolic blood pressure, we have cholesterol level, and of course HbA1c, that's a key biomarker for characterize type 2 diabetes. And also this HDL body mass. And in addition, we also try to get records about the medication that each patient used during these 5 years. So for medication, actually, it turns out there are more than like 100 medications. Some can be monotherapy, combined therapy. So my current, another project, you try to look into the data, try to group this medication. But for this analysis, particular application, we just do very ad hoc grouping, as you can see later. Well, this is just a very brief summarize why people are interested in using EHR data for precision medicine. So the first, obviously, the big benefit of using EHR data is cost effectiveness, right? Because they automatically record in the medical system, computer system, so you can easily extract from the system, and then you get the data. In some sense, like you get the data for free. And the other important thing is this EHR data, they really reflect the real-time and real-world evidence. Usually we don't see this in a lot of standard clinical trial and cohort study, because a lot of standard clinical trial and cohort study, patients enroll into the study under very restricted recruitment criteria. So they not necessarily reflect the whole population in the reality. But you can get this more general information from EHR data. And also, if you do a good job with analyzing EHR data, you have a very good opportunity to understand disease progression and also understand the heterogeneity within patients, so that you can get a better disease prognosis and the treatment optimization as well. And of course, the last point is always talk about this big data thing related to the volume of data, variety of data, veracity of data, and also there are other V's I didn't list here. So there are two specific goals we want to do here. I mean, I mentioned earlier, our eventual goal is want to use this data, real data evidence, try to learn optimal treatment rule, try to treat type 2 diabetes patients. But there are two specific goals we want to achieve during this task. The first one is, how can we use the data we get from this medical record system and to try to understand the heterogeneity among the patients. You know, patients are very different, right? So you will want to see what's the structure, what's there's might be some group of patients very different from other group, and maybe you should think about different treatment between this group and the other one. And the second goal, of course, if we know the subgroup or heterogeneity among patients, how are we going to incorporate the information? We try to find the optimal treatment rule decision. So when I say what's optimal treatment rule, really means we try to control HbA1c level in this case. So just for your knowledge, we know like a normal people like HbA1c should be below 6.0%. Pre-diabetes is 6 to 6.4%, and the diabetes is about like 6.5%. But in reality, for type 2 patients, the level can be 8% or 9%, as you can see in the data. Well, I mean, the one big challenge to try to analyze EHR data is you need to have very good and then no ambiguity definition of time window, because it's not like either core study or clinical trial. You have time zero, right? Like at the time you recruit the patients and the patient come to a study. But EHR data is just a pick like a current window 2013, 2017. So you decide what kind of time window you want to use for each analysis. So I give a table here, which I'm going to show this table again later. And the base of this table is based on current time window. I should say like this is not the best way to try to divide the data, but this is I think this is a reasonable way, because this is non-informative, right? So current time window is just current time. It's nothing to do with each individual information. So now there's 4 windows we divided here. So first the 3 window, like a 2013 to 2016, we basically is a 36-month data. We use this kind of data, try to extract some latent feature about the patients. So why we use this long window? Because we're going to use all these longitudinal biomarker collected over 3 years. So from that kind of very long window, we can understand what's kind of long-term latency among the patients. But in addition, we also use like 2015, 2016, this is 1 year window, which is a very short window. Try to extract feature variable about the most recent like health status about each patient. So you can see like first 3 window is long window, so you can see some long-term latency about the patients. So hopefully you can get some feature or some structure which you cannot see within 1 year window. But in the same time, we still keep most recent health information as a feature variable, which we're going to help us make a treatment decision. Well, of course, like when you try to make a treatment decision, you need to have some time point, say, okay, when you're going to use this drug and the other drug, right? So basically it's like a time zero in the standard clinical trials. So let's say what we have this kind of baseline treatment date, and sometimes the people call it index date. So in this data, basically we use last clinical visit, last clinical encounter of the patient as time zero, as basically like the treatment, the drug they receive at this time will be treated as a treatment assigned at time zero. Okay, so and of course after this this encounter, we basically go into like 2016 to 17. This kind of data is like a post-treatment, right? Because when you make a treatment decision, you try to learn treatment rule, you have treatment phase, you need to know what kind of happened after a patient get treated. So we use this 1 year window, basically after 2016. try to define what kind of outcome. In this case, is HbA1c level change. We're going to use this data, try to extract this information. So that's kind of how we set up a problem. So to summarize, basically this is the 5-year window data, but we're going to use the first 3-year window, try to extract the long-term latent features about the patients. We use 1-year window, 2015 to 2016, try to get their more recent health state. So we can use this kind of state variable as a kind of decision when you make a treatment decision. And treatment decision, treatment data is last visit in 2016. And all the information up to end of 2016, we're going to use, try to define what kind of outcome we're going to use. So, so this is kind of how we set up a problem. So we have data like this, and then we have this kind of plan. And our goal again is try to learn optimal treatment rule for treating this type 2W patients. However, there's some challenge in the EHR data. So data are cost effective to get, is a cheap data, but always there are a lot of noise. There are not just challenging we need to deal with. And I mentioned this particular time challenge, we see this kind of data. First, the biomarkers. Remember where I mentioned earlier, we get records of biomarker like blood pressure, we get BMI, we get a medication use over 3 years, right? Those biomarker measurements, they are multivariate, obviously. There are many different biomarkers measured longitudinally over time. They are mixed types. Think about some lab measurements that are continuous, like blood pressure is continuous, but there's some diagnostic code that can be binary. So they can be binary, like if they prescribe this or not. And they also could be in medication is counter data. So in other words, it can be any like a type like continuous, binary, or counter data. So when you have biomarker like data or like your variable like this, how are you going to integrate them together? Try to become very useful feature you can use for treatment decision. Obviously, there's a simple way, you just take summation, doesn't make sense because they're on different scale, they're different type of data. You cannot just simply take a summation or take some simple mathematical algebra to do that, right? So that's the first challenge. And the second challenge is the biomarker data that collected at each clinical encounter. And they're very irregular. When I say irregular, which means, you can see some patients, the measurements maybe take within this 3-year window, maybe they have to like 2 or 3 records, but some patients maybe have 20 or 30, and they happen everywhere. It's not like a regular, fixed number of time points. It happens everywhere. It's pretty random, which I'm going to show you further very soon. So this is the second challenge. So yeah, if the data are collected so irregular, how are you going to put the information across patients to come up with a reasonable variable which you can use for the future analysis, right? So this is like a not structured data. It's not like a metrics data given to you. And the measurement, the third point is measurement time points is very heterogeneous across patients, and then they're informative. Because you only collect data, most time you only collect data at the clinical encounters. Why they go to clinical encounter? Sometimes maybe by schedule, but another case is the patients don't feel well, they get bad, they go to hospital, they go to clinic, and the clinic they take measurements, right? So it basically means the time points you take measurements are informative about the health of the patients. So whenever you try to do the analysis, you try to extract information or for future for prediction purpose, you need to worry about this because the data basically is you sample data in some biased way. It's not like a purely random across time points. And also treatment are many, and there's huge significant like a difference between treatment groups, which we're going to consider later. Well, so this is a snapshot from this data. I took a snapshot like about 20 patients here, and each this short mark, this vertical mark basically tells when they take a measurement. The time 0 basically is the calendar time, 2013. So, and you can see for each patient, when they take a measurement is so different, right? You can see first patient is like a measurement only after like 600 days. But last patient, you can see measurement almost everywhere. And even for different biomarker, the measurements are very different. You know, like say, you can, as you can see a lot of pink mark. Basically, they correspond to medications. So in other words, looks like most time they get the measurements is about the medication. But some measurements like HBP, HDL, you probably don't see a lot here. Almost, yeah, you can see a few places down there, but not many. So there's a huge heterogeneity about the measurement time points across patients. And then even within the same patients, there's a huge heterogeneity across different biomarkers. And how are we going to consider this issue? How we account for this issue when you do analysis? If you don't do that, you can imagine, for suppose you ignore this issue, it just do simple analysis. Then your analysis results will be mostly driven by the patients with the most with a large number of visits, measurements, right? And then your analysis will be driven by the biomarker, which has a lot of measurements, which in this case is number of medications. We don't want that to happen because with this, we need to correct this sort of bias within the data. Well, this just shows like a counter of different medications. So you can see majority medication taken by this type of patients like insulin and metformin, but there are other like immunotherapy and also combined medication, which I didn't include here. Actually, there are more than 100. But this just demonstrates to show you that insulin and metformin are most prevalent medication used for this group of patients. All right, so then my first thing is try to use some statistical modeling, try to integrate this longitudinal biomarker together so that we can learn some long-term latent structure about these patients before we even develop a treatment decision. And why we want to use statistical models? Because I mean, I'm a statistician, I mean, or many of you are statisticians too. The statistical model advantage is they can really understand, try to model the mechanism behind the data process, right? Because we model the distribution. So we use a statistical model, we can see how data really come out, right? And if you use a good statistical model, you should be able to integrate all these kind of different biomarkers, even though there are different types, they are measured at different time points, and their time points are very informative and they're very different across patients. But everybody can be integrated or unified into one statistical modeling process. And then once you do that, then you can use this model, try to combine the information and extract the information you want. So for this kind of analysis, as I said earlier, so we use the 3-year window data. That's like from 2013, 2016. And they include this about almost like 8,000 patients. And we can use that data and feeding out the statistical models and use this model, try to extract the feature. It actually eventually is a subgroup about the patients. And we can use the information later. Well, this little bit of notation, even though I promise I try to avoid too much math notation here. But this notation just simply say, okay, for every patient, let's count data looks like. Well, you have some baseline feature variable or covariates, like demographics, a disease history, right? So I put it like an XI here. And then I mentioned we have this longitudinal biomarker measured at different time points. So this Y basically denote the different type of longitudinal biomarker. And then in your mind, you can think about example, like I say, Y can be blood pressure, right? And there can be like number of medications. And also can be like a A1C level over time. So this based on, but this just show you like this biomarker measurement only take very different time points T. So that's IKL. This just show like a different biomarker may have different time points for measurements. Well, the first thing, remember there's a first challenge is those biomarkers are different type, right? They're continuous binary count data. And how we're gonna put them together so then we can integrate them together and then come up with a nice feature we can use. So what we do here is we can treat it all come from this called exponential family, basically like a statistic, right? Statistically, people use this exponential family to model different type of variable. Can be continuous, basic normal distribution, binary, usually it's end up a logistical model, right? And the count the data basically from exponential family end up with this Poisson model. And then we can put them all together. And then when you specify this exponential family model, one thing is that there's they call it canonical link function, and that try to relay your covariance in this X to your each biomarker. And then let's basically like standard like generalize linear mixing model we do it. Except one thing is we have this latent process I call epsilon t. So basically what we are assuming here is your each individual longitudinal biomarker, like the generalized, they come from this we call it generalized linear non-linear generalized mixed effect model. But this mixed effect depends on latent process epsilon t. And this epsilon t is like a normal basically it's like a Gaussian process. You can think about that way. And you can see each biomarker have this latent process. So if you have a K biomarker, you have 10 biomarkers, they have 10 latent process. And of course, they're not independent, right? They're dependent. So you can see I introduced this covariance matrix, try to capture the dependence between this like 10 biomarkers. And also I allow this time-dependent coefficient to reflect the time-dependent effects of covariance. But this is not essential, but you can make it time independent if the data show is time independent. But main thing I really want to emphasize this latent process. First, we introduce the latent process so that you can capture the dependence between biomarkers. And the second thing is this latent process basically is like continuous process, right? So basically this means even though each biomarker have very different type, one is continuous binary count, but after this exponential family projection, we can project them onto this latent process, which is on the same scale, on the continuous scale. So basically means that each biomarker has a latent process, but this latent process is multivariate Gaussian, and they're on the same scale. What's good thing about some scale? Because once they're on the same scale, they're continuous like epsilon t, we can combine them, right? You can take summation, you can take average, you can take whatever, right? You cannot combine original biomarker, it doesn't make sense. One is continuous binary, but once you project on this latent continuous process, you can combine them. And how we combine later, we're going to define so like a distance, how to combine them. And the one thing I also mentioned, like we allow this covariance matrix, basically dependence between biomarkers, let me change it over time, t. So this basically this just summarizes this kind of joint model or latent process statistical modeling how useful it can be. First, what we allow this time-dependent beta t and omega t, right? Basically, the effect can change over time t, and the dependence correlation between biomarker change over time t. But most important thing is we essentially project each biomarker onto latent process epsilon t, and then on the same scale they have this multivariate Gaussian distribution. And once on the same scale, combined the original biomarker can be transformed into combine this latent process, which is easy to combine because it's continuous variable. Okay, and also I mentioned like this the covariance matrix is pretty unspecified. We don't allow some structure about this covariance, try to improve like model robustness. So, well, so you can see by this model, we handle two challenges, right? One first I mentioned is the biomarker different type. You use the latent process, you can put them on the same scale. And the second challenge, they are this irregular, not at random, which is fine because even the measurement for each biomarker is not on the same time. But once you even for this latent process, basically you get a latent process for all the time, right? So this is the second challenge we already handled. What about third one? Third one is about this measurement time point, right? Measurement time point is informative because we only take measurements at the clinical encounters. So how we do that? Well, this is like a time, like an event time process, basically like when they're going to take event is not easy informative. So to do that, we introduce counting process notation. But if you don't know this event time data analysis, you can ignore. Basically, it's kind of process to tell when this measurement is going to take it. And to account for this informativeness, we have this model, that kind of intensity model, try to model this process, which is given in this equation. And this model, basically, you can see like different patients or different biomarker. This process going to depend on this patient's characteristics and depend on the past measurement biomarker measurements, right? Because there's a heterogeneity here, because I just we saw earlier, the measurement time point can be very different from patient to patient, but even within the same patient, they can be very different from biomarker to biomarker. And then we try to model this way. So from this model, we can understand what's heterogeneity due to. It's due to X, well, different patients have different baseline variable, right? And they can due to different biomarker history, which is L here. Okay, once you have this knowledge about this X effect, L effect, the next thing we're going to do is we're going to do sort of like a normalization on this time measurement process. What we do is simple this equation. So you can see original time measure process is this DNIKT, right? And then we know this DNIKT depend on this one. So this one causes a difference between patients and causes a difference between biomarkers. So what we do is just simple, just divide this term from this DNIKT. So it's like a normalization. Because you can imagine, once you divide this term, you get this new process, I call it new time measurement process. They're going to be independent of X, independent of biomarker history. What does independent imply? Basically means use under this normalized counting process or event time process. Every time measurement time points, they're homogeneous. You don't have heterogeneity anymore because we remove them from here. Okay, so this is the kind of idea when you introduce this kind of, this is a very popular model, intensity model usually in a lot of event time data analysis. Is also one commonly used statistical model. So we use this kind of statistical model, we can remove the heterogeneity in a time-dependent measurement process. And then even later, we're going to just use this process to capture time behavior. Okay, so this is just kind of like an idea behind this approach to handle the challenge when you have this kind of longitudinal biomarker, as we always see in the EHR data. So, so next few steps basically just show how we're going to do statistical estimation. Data is very sparse, again, we know that. So we're going to use a local smoothing, try to, and based on method moments, try to estimate quantity based in those models. You remember we have these coefficients, we have covariance metrics, we need to estimate. So I'm not going to get into detail about here, but essential idea is use kernel smoothing and basically borrow information from neighbor, but also across all the patients. And they're going to help you estimate your beta. And the next one is estimate your covariance metrics as omega. There is right here. Yeah. So, but one thing you can see, well, you don't have to get the detail about this this estimate equation. But the main thing I just show you here is we use this normalized counting process, a normalized event time measurement process. And again, this is just what I said earlier. Use a normalized version, you can remove heterogeneity about these time measurements across all the patients and also across all the biomarkers. Then you don't have the bias because once everybody is standardized on the same process, right? Then the bias is gone. Okay, so this just a kind of little bit detail about how we do estimation, how we're going to do inference. And also this is about detail how to choose a bandwidth. And actually interesting, because we do this local smoothing, right? It's kind of smoothing, you need to decide the bandwidth, what kind of local you're gonna use. And we choose this bandwidth based on bias and the variance trade-off. Let's people know that from this kernel regression, bandwidth, you're going to have a trade-off between bias and the variance. And then we use data empirically, try to estimate bias and try to assess the variability. And from there, we find out what's optimal bandwidth. Well, this is just some theoretical results about the asymptotics, so I don't have to say that. Okay, so you can see after you fit in this model, basically you use a statistical modeling, and essentially you project all of this longitudinal biomarker process on this latent process, and they are correlated. We know they're omega, right, which is correlation metrics. And next thing is how we going to put all this information together, right? Well, of course, you can still put this whole latent process into a feature variable, but usually I don't want to do that. I want to just extract some very few feature variable, which we think are important, and which capture heterogeneity among the patients that I can use in the treatment decision later. And then here we do very simple one. So first use this joint model framework, because statistical model, once you have a joint model, you can infer what's a latent process. That's the advantage about the statistical modeling, because you remodel the mechanism, model distribution process, right? And use this distribution mechanism, you can understand what's latent one. And then once you get latent process, I call it epsilon t, and then we already know that's correlation, right? Then we can simply calculate this Mahalanobis distance, basically is given by this form. And then basically we can, from here, this distance basically capture patient I and the patient J, how similar they are in terms of their longitudinal biomarker in the history. Make sense? So we use longitudinal biomarker, we infer latent process, and then from this process, we use the correlation matrix, and then we can capture how similarity among all the patients. Use similarity this matrix, obviously, then you can do this cluster analysis, right? You know, when we do cluster analysis, the reason we do cluster analysis is we want to study pattern of the patients. And the same thing, when we do cluster analysis, we have this similarity matrix, and then you can try to find the cluster to see which kind of patients they like to belong to the same cluster. And the same cluster means what? Basically means there are historical EHR, this longitudinal biomarker, like a blood pressure medication use, or all other kind of biomarker, they look similar. They have similar pattern or similar trend. So that basically those patients have similar like a disease history in that sense. Okay, so once we have a cluster, and suppose I cluster patients into this number group, and then what I'm going to do treatment rule, I basically go to each individual cluster and try to learn treatment rule. Then basically let's move to the next step. How are we going to do an optimal treatment rule? And in this case, we rely on machine learning. So previously is because data complexity, nothing can be normalized, can be standardized. You rely on statistical models. But next step, I'm going to use machine learning to learn optimal treatment rule. Now, why we want to use machine learning for this context? Because as we're going to see that soon, the treatment rule essentially try to optimize, we call it value function. Basically, it's like a benefit. Like say, suppose I give this kind of decision rule to future patients, I want to max their benefit. In our example, basically, I want to control their HbA1c level below certain threshold. And because the goal is try to optimize, maximize some value function, or the other way is minimize some loss function. So that's very naturally related to machine learning. That's whole machine learning and whole idea behind it, right? Machine learning basically is saying, you try to do something, find a prediction rule, classification rule, you try to optimize certain object function. Forget about distribution, forget about how data are generated. It's very direct. So that's why in this context, machine learning is more powerful and more robust because they don't need to specify modeling, distribution, or this kind of thing. Right? Okay, so to do this, while we already have this latent group clusters I mentioned from this 3-year window data, right? And I'm going to add more feature variable. Obviously, you're going to add this demographic variable. But also, I mentioned earlier, we're going to use a 1-year window to capture this short-term disease biomarkers. So basically, like I say, in the past year, what's average value blood pressure, what's average value of cholesterol level, HbA1c level, or something. So we can use this short-term feature variable as part of decision. So this is a 1-year window. We're going to extract this short-term. Well, we also need to define, remember, we already have this treatment time 0, right? I mentioned like a last clinical encounter date as time 0 for treatment. Then, but you need to define your outcome. And then your outcome for our case is, in this case, is a 6-month HbA1c level. We want to say, if I give a medication here in 6 months, what's the HbA1c level in 6 months? Okay, but the post treatment for the EHR data, nobody can have I mean, not everyone have a measurement at 6 months. Actually, it's everywhere. You know, Sometimes they get a measurement 3 months, 12 months, or 1 year, maybe even just only like one record after 1 year or something. So in that case, you need to use the data, try to define well your outcome. You cannot use a 6 months A1C level, but the other patient use 12 months A1C level. It is not comparable. So what we do is we do sort of like interpretation. So we use this post-treatment data, and I think we just find the linear mix type of effect model, and we use that model and try to predict what's a 6 month value, and use that one as our comparable. Well, which is not an ideal way. Ideal way we should get exact measurement at 6 months. But unfortunately, EHR data, that's a challenge because nobody gonna say, oh, I'm gonna come exactly at 6 months, ask you to take a measurement. Well, I mentioned medication will be more than 100, but for us, this illustration, we only group it into 4. One is metformin insulin, and the other mono type 2 diabetes therapy. But the last group is more than 1 medications. And I mentioned another project we are doing now is let data tell us how to group in this variable. But this is just based on clinical meaningful definitions. Okay, so this is the window 2016, 2017 post-treatment. That's the kind of window data we're going to use, try to calculate the outcome. Basically HbA1c level in 6 months after treatment. All right, so once you have that, then you have a feature variable in the treatment. You have medication, which is one of 4 groups, right? 4 treatment groups. Then you have a 6 month outcome variable. Then you get a very structured data, very nice structured data. Then the next thing you're going to use machine learning. In our case, use machine learning to learn optimal treatment rule. Well, to understand what's treatment rule, basically is a kind of decision function. Basically, mapping a feature variable or like covariance at the treatment and into one of a treatment choice. In this case, we have 4 treatment, right? Insulin, metformin, and other treatment therapy. And this Z, remember Z is a feature variable, basically include those cluster ID we learned from this 3-year window, right? Using this statistical model, but also include the baseline variable and include like short-term feature variable, which I mentioned earlier, like just 1 year average of biomarkers. So Z include all these bunch of variables. And we want to find some function or some map. You give me one Z, you know patient's Z, you want to give a treatment recommendation. Should be 1, 2, okay. Well, observation study, there's no way you can get around this like a propensity score thing, right? Because pure observation is not randomized. If we randomize it, totally fine. Observation study, you need to understand what kind of patients like to receive insulin, what kind of patients like to receive metformin in this study. And then once you have this kind of propensity score thing, and this is a value definition associated with this decision. So in other words, if you have this kind of treatment decision or rule, this is what expect the value, expect the benefit given by this expression. And then you can see I use negative R because R is A1C level. We want the R smaller the better. So that's why I use negative. Okay, so to do this one, okay, so come back to here. So you can see the optimal rule essentially is trying to maximize this value function. Let's kind of echo what I said earlier, because the goal is very simple. It's just maximize this value function, find optimal treatment rule for me, right? So I'm not interested in what's the distribution, how treatment interact with Z, how there's any causal pathway here. No, I'm not interested in this mechanistic thing. I'm just need to say, tell me how to maximize this and give me optimal treatment rule. So from this kind of point of view, I feel like that's kind of very well aligned with machine learning, right? Because the whole goal is give me one object function or loss function, how you minimize or how optimize and give classification rule or prediction rule. So that's why we use machine learning in this context. Well, we use gradient boosting to estimate propensity scores. I don't have to say too much, but everyone knows about that. And then the thing here is we use the calculate prognostic score. Basically, we get a propensity score, which tells me what kind of patients like to get a treatment 1, 2, or 3, or 4. But we also get this prognostic score, which tells me which patients like tend to be high risk or low risk for this type 2 diabetes. So basically, it's how they relate to HbA1c level. And once you have these two scores are very important because they can correlate it with their treatment effect for each individual patients. So once you have this score and you have this feature variable, and the machine learning we take here is based on our earlier work, we call it matched learning. Matched learning idea is, well, I mean, a lot of cases, like people do this optimal treatment rule, and for this one, they're going to rely on minimize the like empirical part of this one. So basically, they call the inverse probability weighting. You know, that's because there's a propensity score in the denominator. But we know in observation study, this probability usually very, very small, can be very, very small. So if you have very small probability in the denominator, the computationally will blow up your computation over. In a lot of cases, you get a non-convergence, and the result can be very variable. So we want to avoid it. And what we do is use matched learning. We're not trying to do this kind of inverse probability weighting. Basically, we try to match the patients. So for example, if I want to compare drug A with drug B, and how I want to see if how drug A is better than drug B, what you can do? You pick one patient with drug A, and then you're going to find another patient with drug B, but they are very similar, right? So let's call them matching, right? We match them, become matched pair, and then based on their response, then I can tell, okay, A is better than B, or B is better than A. So let's kind of idea behind the matching. It's a very popular, well, it's a very popular method in causal inference. You know that. So this kind of, and this approach obviously automatically avoid this weighting. We're not use weighting, we just match. And then you can always use like a one nearest neighborhood matching. You can always find some patient matched to you, right? But the one key thing is a matching is a distance definition. There's a distance, right? You need to tell how similar, what do you mean similarity? And in this case, remember Z have a lot of variable, right? So first is a cluster, we learned from this statistical modeling. So naturally you just match it on a cluster. But second thing, you're also going to match the propensity prognostic score, which I just talked about a couple of slides earlier. Because those scores are very important, are very informative about the treatment decision. One is like say, why this patient get this treatment in practice? Obviously, it's not random, right? It's very informative. And also, what kind of patients is high risk for this disease versus low risk? They also can be informed about treatment response. So those two scores will be included into this matching. And actually, statistical people know if you do this kind of matching, they have this kind of, they call it double robustness property. But I'm not focused on that part. But just telling you, matching on those two scores are very important. Okay, so once we do matching, we do this match supported vector machine, and then we learn optimal treatment rule. So I don't want to get into detail about this one. So, so I'm going to jump to my application part. So, as I mentioned earlier, so we have this data from like a 5-year window. After we remove this missing data, and we go through the criteria about we need to have data like in the 5 year. We end up like 8,000 patients with this kind of longitudinal records. But later, when we do treatment rule, because we see the treatment time will be last visit or 2016, so we end up only like 5,000 patients eventually. And this plot basically show you. Remember when I built up this statistical model framework, we tried to learn this latent process, right? And we want to say different age, gender, this effect, how they affect each biomarker. And this shows like those effect over time. So you can see there's some nonlinear trend, but in general, direction is similar, like they're all either all positive or negative. But you can see some dip in the middle for some biomarker. And this also shows like correlation between these biomarkers. We have this I think 5 biomarkers, and we basically just say, well, which biomarker correlated with which one, and how this correlation changes over time. Now, for example, like HBP, basically high blood pressure, and HDL, they're negatively associated. We know that, right? One is more healthy, higher, more healthy, the other is not. And this is negative on the average, but you can see this correlation tends to increase over time for this case. You can also look at the other biomarkers as well. So once we estimate this correlation, and remember we use this latent process, and then we can infer this latent process and use correlation to define the similarity between patients. and then we can do cluster analysis, right? So this just plot to show you once we have this 8,000 patients, we get their similarity distance, and then we're gonna cluster them into different group, because each cluster tells us, well, maybe for this same cluster, patients have same profile of this longitudinal biomarkers. And from this cluster analysis, you can see different color. We identify 6 clusters. And I put this table here. So you have 6 clusters. Each column is like associated with each cluster. And what I report here is, excuse me, is the average value of each biomarker within each cluster. Okay, but actually this is not like average, it's normalized by the whole data mean. So it's, I should say, average of standardized biomarker value. So for example, like if this is a 0.011, which means it's a little bit above the average of whole data in terms of this biomarker. And I reported the average of for each cluster in terms of each biomarker. So very interesting thing. You can see this 6 group, they're really distinct from each other. They really have 6 patterns of group of patients. So you can see, like, for example, I just pick a 1 here. So for the third column, the group of 3, you can see HbA1c level is much higher compared to average, 1.6. This is a standard, so we divide by standard deviation. Right, but other biomarker you can see not that as high as HbA1c. So which means this group of patients is really diabetic patients. I would say really diabetic with a very high risk for diabetes. But look at the group of 4. Group of other biomarkers is okay, except the HDL is very high, right? 1.679. Remember, this is compared to 0. 0 is average. So which means this group of patients is what? Have very high HDL. Which means they're healthy patients, they're very healthy. Because HDL higher, the better, right? And then you can also see other group, like for example, group 5, total cholesterol level is the highest. And the group 6 is a BMI, is obese or more obese patients. So you really do have this kind of very clear pattern. And the interesting thing is even though we get this data from we get this group from the data before 2016, right? And for this data set, we also use the additional data from 2017, 2018, and try to do a similar analysis. We find a similar pattern. So this means like this group pattern is not purely random. Actually, it's we see this pattern over a few years after 2017. So we are confident this pattern is really useful to capture treatment decision. So once we have this subgroup, and we, like as I said, we do matching learning, and this just describes how we do matching, how we analyze data. And then this shows like a propensity score, because as I said, the observation study, there's no way you can avoid the propensity. You need to understand what kind of patients, what's the probability of each patient receive a different treatment. And then you can see it's very different propensity score across treatment, So this just this 6 corresponding to 6 group I mentioned earlier, right? Use a cluster analysis, we have 6 groups. So we looked at each cluster to study the propensity score pattern. Okay, so this table is our final result. So basically, we do this machine learning, we get this optimal treatment rule, right? But obviously, we need to say how good your rule it is, and does it really help or not? So how we get that? So we have to do this kind of cross-validation because there's no external data, even though we try to do external data with Columbia. But right now we just do cross-validation. So we split the data, training data, use our methods, and then go to another data. But after just a bias, we try to report what's the value, in this case, HbA1c level, if we use our treatment decision rule. And then remember, we have 6 different clusters, right? So basically we get a rule for each cluster, and then within each cluster, we calculate the value or HbA1c level from our treatment rule. And then we compare with one size fits all. One size fits all basically means you just say supposedly all use metformin, what's the average A1C level? So, and if they all use insulin, what happens? So that's kind of number you get from empirical data. And then we compare with our things. So you can see in general, our results tends to be smaller than others. That means better, right? Because as I say, A1C level, which means more is smaller, which means we have more control on this A1C level. And then also you can see the like say group of 3, level is A9, is very high. And even we do very best, we think it's best treatment option. You can reduce like 7.7, which is better, but still very high. And why is it high? Because we just saw it before. This group is really diabetic patients. That's why I saw here, right? The group 3, the baseline PNC level is already very high. So that's kind of reflected in this results as well. So this make us feel kind of confident this result may be trustable. And this also shows like a treatment location. So again, you have 6 clusters, and this shows like say count of each treatment assignment in the actual data. So let's look at the group 3. So you can say in the group 3 original data, you have 39% patients that receive insulin only, so it's the highest one. And the next one is like other therapy. Metformin is like only like 14%. But our treatment recommendation, so the bottom one is our treatment recommendation. So basically use our machine learning, we learn treatment rule, and we look at group 3 to see based on our treatment recommendation, how many of them should receive insulin, how many of them should receive metformin. And interesting, we found like most recommendation we suggest is metformin instead of insulin. For other group, while we still see more recommendation for metformin compared to insulin. And then we try to be thinking about this. Well, there's some explanation, but it's not fully satisfied because it's so observational. Maybe there's some historical information we not fully capture, but maybe on the other hand, maybe also suggest a lot of in the practice, patients get an insulin, usually get insulin is because metformin didn't work based on some guideline, let's say, or they should see insulin after. So maybe for that kind of population, we maybe standard practice should then recommend to go to insulin, because insulin is going to increase the adverse event, going to cause a lot of cardiovascular risk. Maybe you should stay with the metformin. So let's kind of think implied from this kind of distribution, which may or may not be true, we don't know. So ideally, hopefully we can get some more conforming data or external validation data to confirm our finding. Okay, so finally, just some conclusions. So we propose this general framework, try to learn this optimal ITR, and our framework try to combine the advantage from statistical modeling, which is can really learn this latent data mechanism, and which are useful to handle very complex data, missing data, measurement error, and the informed missingness, and the different type of data is very useful for that part. But also we combine with the machine learning approach, which is a robust approach because they don't need the modeling. They can just directly give you a solution, right? In this case, they can just directly learn this optimal treatment decision. So we combine those two, and we think that those two actually is not like contradict to each other, it's a complement to each other. Each one has the advantage, but of course there's a limitation as well, right? Statistical modeling, pure usual variable model misspecification, right? Machine learning, of course, is robust, but it may not be efficient. And maybe they don't use like some structure very well when you try to develop this machine learning approach. Okay, so the other thing, like we're going to talk about some extensions. So for example, when I learned this latent process, I really didn't use this temporal correlation. I use correlation cross-sectional, just between biomarker at each time point. The reason we try to not do this temporal correlation, first, of course, modeling this temporal correlation is complicated. And the second one is computation challenge. Once you incorporate temporal correlation, you can learn better clustering, right? Because you're going to capture temporal change or in the latent process, but computation will be challenged. And also, like as I mentioned earlier, even though we find this ITR in the cross-validation version, it tends to be superior than one size fits all, but we still need to worry about, can we validate it using external data? And the last thing is, can we look into multiple outcomes instead of one single outcome? And then, like, for example, some currently ongoing project, we're looking at this kind of benefit risk trade-off. So we want to control A1C level, but you will be, as I said earlier, a lot of drug, if you control HbA1c level, you're going to increase cardiovascular risk. Like hypoglycemia. That's a very big problem in the treating type 2 diabetic patients. Well, we only do one time point treatment decision, but my own research is also thinking about this dynamic treatment. So in other words, we're going to make a decision over time. So say if this drug doesn't work, should we switch? Should we increase intensity of a dose, or should we stay on the same drug? So let's kind of dynamic treatment regimen. And that will be even more complicated when you have the EHR data, because data will be even sparse, irregular, and how you define multiple stage is also a big issue in this case. So again, this is not one single one, it's a teamwork actually. And as I mentioned, we use the data from Ohio State. So let's my collaborator from Ohio State, and he has a very nice team, including clinician, and she helped a lot about how we get a biomarker, how we get each definition very well, and how we get the data from data warehouse. And he also has an informatics team try to help us to clean the data, process data. And Jitong is our former student, and he do all this programming. And Yuanjia is my collaborator. And right now we are trying to think about use this approach, try to get external validation, use the Columbia EHR data. So I think, thank you. I think I got stop here.
Thank you, Dr. Zeng, for the interesting talk. Anyone has questions? Okay, so maybe I can ask you a question. So when you talk about normalization counting process, you use the ratio, like the count divided by X beta. But if you do the, I think it's very early.
Yeah.
Oh, why not? Yeah, it's right here. But if you just do subtraction, the difference, is it something like residual?
Yeah, well, if you do subtraction, it's not like, well, it's not residual. It's just the only thing is, this is like intensity. Basically, is kind of like a density, basically like a density. Mm-hmm. And this is a common baseline, so base common density. Mm-hmm. And this part, because this part going to with the counter process effect density through this multiplicative scale. So it's a multiply. So what we really need to do, if we really want to remove the heterogeneity, we want to make this intensity or density nothing to do with X, nothing to do with L. So in that case, because it's multiplicative, so if you do this kind of division or ratio, then basically this term will be removed from this like a density or intensity. Then basically make the intensity homogeneous. Then you don't have this heterogeneity going.
Okay, so if you remove the effect of X, but when you cluster and see the difference, similar between patients, and you group the patient into 6 clusters, so the grouping is not based on X anymore because you remove the effect of X.
Yeah, the cluster analysis is based on this latent process, right? So because this latent process, or it's this model, so X is already. X is like orthogonal to this latent process. So in some sense, latent process, you can imagine it's some latent disease process which cannot be explained by X. So you can think about it that way. So when we do cluster analysis, we try basically just cluster this epsilon, this latent process. But later, when we try to divide treatment decision rule, we still keep X in the decision. So in other words, the cluster is just provided some additional structure for the patients in addition to X.
I see. Okay. And also at the beginning of your talk, you mentioned for EHR data, and some people maybe have more measurement compared to other people. And if you do it naively, you can make more use of the people with more data points. But if you model this like joint modeling all these biomarkers, so that kind of bias can be removed. Can you explain something to intuition why the bias can be removed?
Actually, it's related to the comment just asked the first question, is the intensity. This one, yeah. So some patients have more measurement, or biomarker has more measurements. It's basically it's going to reflect in this term, So this kind of capture heterogeneity between the patients and between biomarkers. So if we remove this through this kind of ratio, then basically we make everybody look similar. Everybody looks similar. Every biomarker looks similar. So yeah, with more measurement, it will reflect in this intensity. If your intensity is high, which means you can see a lot of time points. If intensity is low, you can see fewer. But if you normalize, then basically time frequency, this kind of for each biomarker, each patient will be look at homogeneous, will be very similar.
I see. So after normalization, this bias is removed because they all have the same, because it's divided by the axis. Yeah. Axis actually measure longitudinal, has the different time points in it.
Yeah. Yeah.
Okay. Thank you. I also have had a question about time varying treatment, but you already said it's quite complicated to do because right now you had the last contact 2016 as baseline, but the treatment can vary over time and also switching. So doing that is actually extremely hard with the EHR data because
it is. That's true. Yeah, I mean, because like EHR, forget about this sparse longitudinal biomarker, adverse events, all this kind of issue. But also even like intensive timing. I mean, time is a big deal. Like I say, you have a treatment right now, and the next treatment is like 6 months, for example. Mm-hmm. But for the other patient, they have same time right now, but next treatment maybe is 12 months. And then why they get 6 months, why I get 6 months, he get like a 12 months. Maybe it depends on a lot of things. So also you need to worry about this kind of issue when you try to think about treatment strategy for next time point, because how we define next stage is very different from patient to patient. So like I said, in this context, it's not like the dynamic regimen is not just only prescribed like a drug, right? Say drug, so metformin, insulin, but also the question is when you're going to give, right? Mm-hmm. You're going to give earlier. You want to like say monitor patients, like I say blood pressure, or of course blood pressure. I just use my example, and to say at some point if blood pressure is higher than this threshold, I should give a drug, or you should wait. That's a very complicated issue. And the EHR, you obviously need to abandon the data to be able to gather all this information.
I see. So out of curiosity, because you're going to, the timing is also important. And also there's a potential for censoring, right? What if patient only have 3 months follow-up after the baseline? You don't have the chance to observe the next treatment. So this is another complex.
Yeah, it is. Then this can relate to informed censoring. Obviously, informed censoring have been treated very well in statistical modeling because they can model censoring time, same like intensity I'm doing here. And then they can incorporate it into their framework. Mm-hmm. But in this case, we haven't done that. Yeah.
Okay. Yeah, it is very interesting. I think very useful in practice. Thank you again for the nice talk.
All right.
And
thank you.
Yeah, thank you everyone for joining the seminar. Okay.
All right. Take care.
Bye-bye.
Bye-bye.